Hey guys, thanks for tuning into CMTEQ channel. This is tutorial 4 on electrical power distribution. Now, as an electrical engineer or an electrician, you understand very well that an efficient power distribution is so much important because you need an efficient distribution system that will withstand all your consumer demand. So in this tutorial, we're going to see how a two-wire distributor is used to distribute power from one end to another. So the problem statement goes as follow. We've got a two-wire distributor that is fed at one end, right? And it supplies a load A of 70 amp at 200 meters. So this load is situated at 200 meters, right? And there is another load B of 50 amps, smaller load, at 300 meters. Now this load is situated 300 meters from the feeding end, which means this load A is at 200 meters. So that basically means the entire distributor network is 300 meters long. Now the cross-sectional area of each conductor is 75 millimeter square and the resistivity of the copper is 0.018 micrometer. Now these two parameters here are going to be important for us to calculate the resistance of the cable. Now, if the voltage across load A is 250 volt, we now have to calculate the voltages at the feeding point and across B. So what they've basically done here is they're just giving us a voltage here of 250 volt, which is where at this load here, load A, right? That's a voltage. But they're not telling us what is the input voltage that is at the feeding end and what is the voltage on load B. So we need to now do the work to find that voltage. And obviously, the first thing to do here is to draw the schematic diagram or the network diagram for our system. So I'm going to go ahead and draw my network diagram. And guys, if you find this tutorial useful, if you like it, please subscribe to CMTEQ channel and hit the like button. That will be highly appreciated. So this is a two-wire distributor. So I've got my two wires here. And this is point A because they told me that point A is situated where? At 200 meters. So this distance here is supposed to be 200 meters. All right, then at point A we've got what? We've got a load. So I'm gonna draw my load here, and this load is supposed to be 70 amp. Then we carry on. Then they're now saying that there is another load here at point B. So I'm going to place point B here, and this load at point B also have a current that it is drawing, which is 50 amps. Right. Now, we've got a voltage that have been given, which is what? 250 volt on load A. So the voltage here is 250 volt. Now, we do not know what is the voltage on the feeding end, right? So this is supposed to be the voltage on the feeding end, and this voltage is V in, right? V in is unknown, okay? And the load B, right, which is situated at what? 300 meters from where? From the feeding end. So which means this point here is at 300 meters from this point. But there is already a 200 meter there. So which means here we're going to have 100 meters. So the entire distributor got a cable length of 300 meters. So this is basically our network diagram. So we do not know what is the voltage at this point. So we don't know what is VB. VB is unknown, right? And V in is also unknown, but we know what is VA. It is 250 volt. So now we've got some cable parameters here. That will mean we can calculate the resistance along the cable. So which means here, there is a current here that is 70 amp, and there is another current that's going here that is 50 amps. So basically mean we have a current here, IT, right? So I can call IT to be the sum of these two current, which is 120 amps. So that's 70 amp plus 50 amps. So 120 amps is passing through this first section here, and 50 amps on the second section. So we understand that because there is 250 volt here, that means there might have been, or there are some voltages that got dropped at the section here. So if we take this voltage and we add it with this voltage, we should be able to get V in. So first question, 1, if we say that V in here, right, is equal to the voltage drop here. So we're going to call it V drop at what? At 200 meters plus VA. So this is going to give us V in. But now we do not have the voltage drop. Well, we know that the voltage drop, right, V drop, is proportional to the current that is flowing, that is IT, times the resistance of that particular cable, right? So that is going to be R 200 meters. Now, what is R 200 meters? Now, we can use the RDC, the DC parameter resistance, so that we can find the resistance of this cable, because this is a DC distributor. So RDC is going to be equal to rho here, which is the resistivity of the material that's being used here. We know that it's copper cable. We're not using aluminum cable, it's copper cable. So we got that must multiply the length of the cable, and we must divide it with what? The area of the cable. This is going to give us a resistor. So we can go ahead and calculate this resistor here for that section. So replacing the parameter 0,18 times 10 to the power minus 6 ohm meter, right, times the length 200 meters. Now this is now divided by the area, which is 75 millimeter square. So that is 75 times 10 to the power minus 6 meter square. Now we can see that this meter and this meter will give us meter square, and they will both cancel with this meter. 10 to the power minus 6 will cancel with this one. So we only have 0,018 that we need to calculate. 0,018 times 200, and the whole thing must be divided by 75. So we find a resistance here that is equal to 0,048 ohm. Now, this resistance that we just found, is from a single cable going like this. But because it's a two-wire distributor, so we need to times this resistance. So then we can say that R 200 meters. R 200 meters is 0,048 times 2, and this gives us 0,096 ohm. Okay, now that we've got the R 200 meters, we can go ahead and calculate the voltage drop on that section. So this means that V drop on the 200 meters cable is going to be the current 120 times 0,096. How much is that? And that is equal to 11.52 volt. So this is the voltage drop across the section of the cable. So now we can go ahead and calculate our input voltage. So V in is then going to be that volt drop that we just found, 11.52 plus what? The voltage that is now at this point here, because this voltage here, the 250, is coming from here. But it's only 250, so some go drop along the way. So we're going to add that voltage there, plus the voltage drop. And this is going to be 261. Right, so 261.52 volt. So this is the voltage at the feeding end. So this voltage here, now we know it is equal to 261.52 volt. Now we know what this voltage is. It's no longer an unknown to us. Now that we know that voltage, we can then go ahead try to find this voltage. Now this voltage is as a result of what's coming from this point here minus the drop here at 100 meters. So since we know that the drop at 200 meters give us 0.096, so basically the drop at 100 meters will just be this here divided by 2. So we can then just go ahead and deduce that R 100 meters, right, because this section is 100 meters, it is going to be equal to 0.096 ohm divided by 2, and that will just give us 0.48 ohm. So that's the resistance on that section. Now we can go ahead and calculate our V drop. So V drop, what? 100 meters is going to be equal to the current. Now the current flowing onto the 100 meters is 50 amps, so it's 50 times what? 0.048. And this is going to give us 0.048 times 50, and that is 2.4 volt. So we get 2.4 volt dropping on the section of the cable. So now we can go ahead and find the voltage at this point. So that will be VB is going to be VA minus V drop, right? The V drop of 100 meters section. So that's going to be 250, obviously, minus 2.4 volt, and it gives us 247.6 volt. So the last question, now we've got this is 247.6 volt. So now we can find now the last question, which is the total power wasted in the cable. So that is the power wasted in this section, power on the 200 meters, and also power on the 100 meters section of the cable, right? Because there are different current flowing through those sections, so which means the power will be different. So we can say P total here is going to be P on the 200 meters plus P on the 100 meters. Okay, so we know that power is the voltage times the current. So that will be the voltage. Which voltage? So that will be the voltage drop. So we can say this power P 200 meters is going to be the voltage drop across the 200 meters. That is 11.52. So that is 11.52 volt, right? Times the current on that section, we know it's 120 amp. Plus power through the 100 meter sections, so that is 2.4 volt. 2.4 volt times the current on that section is 50 amps. Now we can go ahead and calculate. So 11.52 times 120, and this gives me 1382 watt, 4 volt ampere or watt, plus the other one is 2.4 times 50, and that is 120 VA or 120 watt. Now we can just add these two current, so that's going to be So that is 1502.4 watt. Or we can simply deduce that it is 1,502 kilowatt. So this is the power that is wasted in this distribution line. So thank you guys for watching. If you've liked this tutorial, you find anything useful, please subscribe and give it a thumbs up. Much appreciated, and stay tuned for more tutorial on power distribution. Until next time, cheers.